Welcome to another fantastic lesson on exponential functions, growth, and decay. Brought to you by your one and only Mr. McNally. Hope you enjoy. The objective today is to write and evaluate exponential expressions to model growth and decay situations. The vocabulary we're going to learn is exponential function, base, asymptote, exponential growth, exponential decay, end behavior, and compound interest. To start the lesson off, let's take a look at this example. In a lab, scientists observe bacteria growing in a petri dish. They notice that the bacteria doubles every hour. There are initially 10 bacteria in the petri dish. Filling out the information below in the table, at hour 0, our population is at 10. It's said to double every hour, so after hour 1, it doubles to 20, hour 2 to 40, hour 3 to 80, and hour 4 doubling to 160. Plotting the points shown at the graph on the right, we get 0, 10, 120, 2, 40, 3, 80, and 4, 160. We get this shape. This is known as an exponential growth function. The definition of an exponential function is any function with the formula of this form: f of x equals ab to the x power. The most important thing about it being an exponential function is that the variable is now the exponent. For this function to exist, the a value cannot equal 0, the b value cannot equal 1, and b has to be strictly positive, or it won't be an exponential function. The a value in this case is known as our initial value. Our b is the growth or decay factor, depending on the problem. There are certain properties we have to talk about with exponential functions. The first main thing we have to discuss is what's called the domain. Domain, you remember, is all the x values, or our inputs. We think of this as what we can sub in for x that always gives us an output. Can we sub in negative values for exponents? Can we sub in 0 for an exponent? Can we sub in positive values? The answer to all this is yes. We can sub in every number that we know. So our domain in this case is all real numbers. We represent it in interval notation as negative infinity to infinity, shown here. We also have to talk about the range of our function. The range is all your outputs, your y values. What is our outputs when we sub in these real numbers? In this case, any number subbing in for x always outputs a positive real number. We represent this as 0 to infinity in interval notation. Another important property we have to discuss is that the graph contains the point 0a and 1b, which is our initial value and growth or decay factor points. The last property is that the graph does not intersect the x-axis. This is known as what's called a horizontal asymptote. You may ask yourself, what is an asymptote? I think of an asymptote as this example: walking halfway to the door. If a person starts at one end of the room and walks halfway to the door at each increment, walking halfway the first time, halfway the second time, walking half the distance to the door the third time, and so forth, the question is, will the person ever reach the door? The answer is no. This is an example of an asymptote. In fact, the definition of an asymptote is a line that the graph approaches but never touches. For our exponential functions, looking at the graph of 10 parentheses 2 to the x power, this is an exponential growth function. The asymptote here would be the x-axis. The line approaches but never touches. There are two types of exponential functions. The first type is called exponential growth. Your a value has to be strictly greater than 0 and b is greater than 1. Examples of exponential growth functions are this. The graph we've already seen before in the lab example. It looks like this. When looking at the graph, we can talk about what's called the end behavior. End behavior of a function is what happens at the ends of the graph as x gets bigger and bigger and bigger, and as x gets smaller and smaller and smaller, more negative. In this case, as x increases in its value, what happens to our outputs? Our f of x actually keeps increasing. So what we say is as x approaches infinity, f of x approaches infinity. What happens at the other end? As x gets more and more negative, and it gets over to this side, what does it approach? It actually approaches our asymptote. So we say, as x approaches negative infinity, f of x approaches 0. The other type of exponential function is exponential decay. The difference between the two is that your b value in this case is strictly between 0 and 1, so fractions and decimals. Examples of exponential decay functions is shown here. The graph looks similar, but looks like this. The end behavior in this case, as x gets bigger and bigger and bigger, it actually switches. In this case, as x increases, your f of x approaches that asymptote, approaches 0. So we say as x approaches infinity, f of x approaches infinity. What happens at the other end? In this case, as x gets more negative, in this case, it approaches infinity. So we say as x approaches negative infinity, f of x approaches infinity. I want you to take a look at this example. I want you to determine whether the given function is exponential growth, decay, or neither. Remember the last definitions on the previous slide. Looking at example A, the b value is 5, which is bigger than 1. So in this case, it's an exponential growth function. Let's take a look at example B. The b value in this case is 0.12. 0.12 is between 0 and 1, therefore it is a decay function. Let's take a look at example C. Is this an exponential growth, decay, or neither? In this case, it's going to be neither. And the reason why is because our exponent is actually a number. Remember, the definition of an exponential function is that the variable has to be the exponent. This is actually a quartic equation, so we'd say it's neither. In the last example in D, our b value is 4/3, which is again bigger than 1, so therefore it is a growth function. One application of exponential growth is what's called compound interest. The formula for compound interest is this: a equals p parenthesis 1 plus r to the t power, where a stands for a total amount, p is our principal amount, r is our interest rate or growth rate, and t of course stands for time. We use this example in a lot of investment problems. For example, let's say you invest $5,000 into a CD that earns 2% interest compounded annually. How much will you have after 10 years? A CD is known as a certificate of deposit. It's different than a savings account. It generally earns more interest rate, but you have to leave it in there for an extended period of time. For example, 5, 10 years, maybe 15 years. Whereas a savings account, you can withdraw or deposit any amount at any time. The question is, how much will you have after 10 years? Subbing in the known information, our principal amount here is actually going to be $5,000. Our interest rate is 2%, but we need to represent that as a decimal, so we move the decimal twice to the left. Plugging in the known information into our formula, we get this. Entering it on the calculator using the appropriate parentheses, our answer should be $6,094.97. This person gained over $1,000 in interest, leaving the $5,000 in the bank for after 10 years. Let's take a look at another example. A certain population of deer has been increasing by 11% each year. The current population of deer in this area is at 400. Which equation below represents the population of deer after t years? Is it A? Is it B? Is it C? Or is it D? You decide. Using the formula from before, we can apply the compound interest to this example. The 1 plus r would be 1 plus 0.11, which simplifies to 1.11. So our answer here is actually B. This would be the equation to describe the population after t years. Another application is on exponential decay model. This is known as depreciation. It's very similar to compound interest except for it's 1 minus r. Again, the variables stand for the same thing. P is the principal amount, r is the interest rate, and t, of course, is time. We use this example for a car situation. Cars are known to depreciate. Let's say a car sells for $22,300 and is known to depreciate at a rate of 11% per year. Find the value of the car after 7 years. Again, subbing in the known information, our principal amount of $22,300, the interest rate of 11%, and 7 years for time, we get an answer of $9,863.59. This is the total of the car after the 7 years. This concludes another fantastic lesson of Mr. McNally's. I hope you enjoyed the lesson. Have a great night. And don't have nightmares from that picture.